Yeah, so this is a question from GATE 2025, and the question is, assume ideal op amps, the circuit represents A. So we need to find or see which sort of circuit is this among the options. So option is summing amplifier, difference amplifier, logarithmic amplifier, and buffer. Okay, so in the circuit we have two op amps, OA1 and OA2. Okay, and the output of OA1 is given as input to the OA2 and its non-inverting terminal, and output of OA2 is given as the input to its inverting terminal of OA1. Okay, so first let us analyze this OA2 circuit. So here the input is actually V out, right, and its inverting terminal is connected to its output. So feedback is actually with gain 1. So this actually represents a voltage follower. Okay, so which means the output of this OA2 is actually V out. Okay, and this means whatever is the output of OA1 is actually again fed back to its inverting terminal, right? So I can draw this circuit as OA1, this is non-inverting terminal, inverting terminal, and it is similar to this one itself, like V out, and V out is directly connected to inverting terminal, right? So this actually represents again a voltage follower, or it acts as a buffer, right? So answer is D. Yeah, so this is again a question from GATE 2025. The question is, the IV characteristics of the element between the nodes X and Y is best depicted by. So we need to find the characteristics, IV characteristic, that is IXY versus the voltage across the XY, that is VXY, right? That is the voltage across these two nodes. Okay, that is VXY. So I need to find the IV characteristics of this. Okay, so from the circuit it's clear that an IXY current is flowing like this, and there is a fixed current source here. So a fixed current 1 ampere will flow like this. So remaining current, according to KCL, the remaining current here will be IXY minus 1 ampere, right? So that is a current flowing through 1K. So what is VXY from this circuit? VXY is actually voltage across 1K. So the current through 1K, that is IXY minus 1 ampere into 1K, that is the voltage VXY. Okay, so here I need to find IXY versus VXY, and the y-axis is everywhere IXY, right? So I'll just rearrange this equation such that I can write IXY in terms of VXY. Okay, so on rearranging, I can write IXY as IXY equal to 1 plus VXY by 1K, or 1 plus 1 milli into VXY, that is IXY. Okay, so here if VXY is equal to 0, what is IXY? IXY equal to 1 ampere, right? And when VXY increases, right, when VXY increases, the IXY also increases from 1, right? So it linearly varies. Okay, so how the output cara will be? So VXY, not output cara, VI characteristics. So VXY versus IXY. So at VXY equal to 0, IXY will be 1, and when VXY increases, it will also linearly increases like this. Okay, so with the slope of 1 milli. So the answer is B. So this is a question from GATE 2025. The question is, in the circuit with ideal devices, the power MOSFET is operated with the duty cycle of 0.4 in a switching cycle with I equal to 10 ampere and voltage V equal to 15 volt. So this I is 10 ampere and voltage V is 15 volt. The power delivered by the current source in watt is dash. So what should be the power delivered? It will be the current sourced by the source into its voltage across the current source, right? So the voltage across this current source is actually the voltage across these two nodes. Okay, so I'll call as a voltage VI, indicating it is a voltage across the current source. Okay, and the question is actually here the power MOSFET is operated with a duty cycle of 0.4. So here we'll say we have the MOSFET switched on like this, right? With a duty cycle of 0.4, which means say this is on time T on and this is off time T off, or and this is total time T, then duty cycle equal to T on by total time T, that is equal to 0.4. That is the given data. Okay, so what happens here? Okay, so when MOSFET is on, okay, what happens? It is like a short circuit here, right? So the voltage VI will be equal to 0, and when MOSFET is off, where this current flow? This current flows through this diode. Okay, so it is like and diode is ideal, right? So diode, through the diode it will flow like this, right? And this 2 is actually open. So what is the voltage here? VI will be same as V equal to 50. This on, this is on, this is off. Okay, so when the MOSFET is on, the voltage across it is actually 0, and when it is off, the voltage across it is actually high, that is equal to 50. Okay, so this is on, this is off, sorry, off and this on. Okay, so here it is 0 volt and here it is 15 volt. Okay, and this is the on time T on, and this is the total time T, right? So this is the voltage VI, we can say. Okay, so I want to find the power delivered by the current source. So this will be equal to the average voltage during this time period T. Okay, VI average into the current sourced by the current source, right? So what is the average voltage here? That is equal to 1 by T, that is the period of this VI into the area under this curve, right? So I can split this into 2 time periods. So 0 to T on, the voltage VI is actually 0, okay, plus from T on to total time T, the voltage is 15, right, dt. So I just need to integrate this. So this is 0 and this is 15 from T on to T, right? So 1 by T, so this is 0, so 0 plus 15 is a constant, and if I integrate this, this will be T minus T on, right? So it is like 15 by T into T minus T on. Okay, so if I take T inside, it is 15 into 1 minus T on by T. Okay, or 15 minus T on by T is 0.4, right? So 15 into 1 minus 0.4, or 15 into 0.6. So this is actually the average voltage. Okay, so what is power? Power delivered by the source is 15 into 0.6, that is the average voltage into 10. So this is equal to 9, and 15 into 0.6 9, and that into 10. So this is actually near to 90 volt. Sorry, 90 watt. So answer is 90.